Which example should we do? Take your pick. Top left. Okay, if we pick the top left, first thing we should go through to do when we're assigning R and S is to identify if we have chiral atoms. Indeed we do. We have two chiral atoms. We'll call them red and we'll call them purple. When we go through to assign, we want to now assign our priorities to all four groups. Typically people miss the fact that there's a hydrogen hiding back there, and that hydrogen is important because that's our fourth group. We then compare that to chlorine and the carbons. Hydrogen has the lowest atomic mass, which means it's going to get the lowest priority. Chlorine has the higher atomic mass, so it's going to get priority number 1. Between the two carbons, we may not be able to tell a difference outright between those. Okay, so we'd move out to the next highest priority atom. When I look at it's my left, that should be your left as well. Leftmost carbon, it goes out to another carbon. If we look at the rightmost carbon, it goes out to a chlorine. Chlorine has a higher atomic mass than carbon, which means the right side has a higher priority than the left side, and we'd get a 2 and a 3. Yeah? We can now loop around 1, 2, 3. Which direction would I be turning? I'd be going clockwise, which makes it R. Before I finalize my answer, the lowest priority must be aimed away from me. The lowest priority being hydrogen in this case, or number 4, is aimed away from me, as I can see by the dash, which means that position is R. If we go through and look at the purple position, we'll see it's very similar. We have now a wedged hydrogen, however. That comes in as a 4, chlorine is a 1. We now have our top carbon and our bottom carbon to contend with. The top carbon goes out to a chlorine, which means it's a higher priority. 2, 3. When I go through to connect, to 2, to 3. Which direction am I turning? Counterclockwise. So I might go through and say S. Okay. Before I immediately jump on that, the lowest priority must be aimed away from me. There are two approaches to how we could go through and solve this. Number 1, we could say, whoops, I screwed up. I can't say that yet. I need to reorient the molecule to get it so the lowest priority is aimed away from me. Okay? Which is fine, and I fully accept that. It's tedious. That's how I always did this. But if we went through and attempted to do that, if we flip across that structure, that top chlorine, so here's my axis again, that top chlorine goes to being dashed. The rightmost chlorine that we'll call on our purple carbon was dashed, but since I'm taking the structure and flipping it over, it now becomes wedged. There's that chlorine. There's that hydrogen. If I go through and assign my priorities, 1, 4, 2, 3, which direction am I turning? Clockwise. Clockwise. R. And my answer is R. If we go through and take a look at it, that's a lot of work to be scribbling down for just a simple 50-50 answer. Unfortunately, that's the only way I've consistently gotten it to work, with one somewhat exception. That one somewhat exception has to do with how I rotated my hand at the end of the last class. Okay, remember last time I said, which way is my hand turning? Which way was it turning? Or which way is it turning? Counterclockwise. And then I had to close my eyes and turn, because at the same time I tend to screw it up. And which way is it turning now? Clockwise. So if we're looking at it from the opposite direction, we get the opposite assignment. If we go back and look at the initial drawing, our hydrogen was aimed at us, meaning we're looking at this molecule from the complete wrong direction. So I can still go through and assign my R and S. I just have to realize that I'm looking at it completely backwards. The S needs to become R, and I achieve the same answer. Okay? Only when the lowest priority is either aimed away from you or at you do I find it to be a trivial assignment. If it's aimed away from you, you just assign it the way it is, because that's how you're supposed to visualize it. When it's aimed at you, it's just the reverse. Right? So I would almost argue that is also trivial. Where it becomes tricky is what if the highest priority is not aimed at or away?
Lowest priority?
Lowest priority, yeah, lowest priority. What if it's not aimed at or away from you?
Now you have to investigate it in 3 dimensions.
You have to investigate that in 3 dimensions. My argument, at least when I went through and did this, and still do, would be to redraw the structure, rotating it so the lowest priority is aimed away from you. I've seen lots of people say, well, if you do this rotation, then it's this, and it just confuses the crap out of me, and I consistently get it wrong. Okay, so if you found some other method that works for you, by all means, feel free to use it. Just realize I've tried a bunch of different methods, and they work half the time. Okay? There's only 2 answers. Okay? So just be aware of that. You had a question, David? Are you good? Okay. Does that make sense? So that one structure was actually 2 questions. We had to assign both of them. Okay? They were both R. Kind of make sense? Your turn. Yeah. Your turn. Yeah. If you got questions, raise your hand. I'll come to you. Do you want me to leave the work up there or erase it all? Leave it? Okay. Okay, so I'm going to pick the lower right-hand corner. Okay, and in fact, I'm not going to do the upper right-hand corner. I'll ask a quick question about that in a little bit after we do the bottom ones. So when we look at the lower right-hand corner, we do have a chiral atom. Okay, one of the things that makes this one a little bit tricky, or there's 2 things that make this one a little tricky. I get a lot of people wondering what the heck this line means. A line has never changed its definition. It's always the same thing. What is a line? A bond. Okay? What is at the end of a line?
Carbons.
Carbons. This is a CH2 and a CH3. Okay? So if it's helpful, you can go through and add those implied atoms. You don't have to just leave it as the line angle. You can add that detail. Okay? The next part that makes this one kind of tricky, is there a hydrogen? No. Okay? Our lowest priority is not hydrogen. Okay? When we're looking at our chiral atoms, typically hydrogen is our lowest priority because hydrogen has the lowest atomic mass. But if hydrogen's not connected, that doesn't mean it's not a chiral atom. It just means hydrogen's not the lowest priority. That's it. Okay? So when I go through and compare, I'm looking at carbon to carbon to carbon to oxygen. Which has the higher atomic mass? Oxygen. It gets the 1. Okay? Common misconception, a lot of people will tell me this carbon is 1. And they'll go, well, isn't this group bigger? I didn't ask about the group. I asked about the atomic mass. The atom that is connected to our chiral carbon is a carbon. That's where my comparison is. I don't care about the size of the group. Okay? So we do have to be a little bit careful with that because that's a common misinterpretation. Okay? If we now go through and look carbon versus carbon versus carbon, there isn't a difference. So we go out from them to the next highest priority atom. So for that top one, we would go out to a carbon. For the bottom one, where do we go? To a hydrogen. Okay? To the last one, we go out to another carbon. Okay? So in our comparison, the lower right-hand corner carbon is the lowest priority. It gets the 4. Okay? We're not still comparing carbon to carbon. Say that again. The lowest priority carbon is the lower right-hand corner. That's our 4. Okay, because it went out to a hydrogen. We still haven't distinguished between the other 2 carbons. Right? They were both CH2s. We went out to a carbon, went out to a carbon. Okay? The next one goes out to an oxygen, and the other one goes out to hydrogen, which has a higher atomic mass. The oxygen, which means the oxygen one is a 2 and a 3. Okay? Kind of makes sense? I need to clean up some of that because I don't want all that work in the way. So now what we could go through and do is assign the RNS. We could go through and say 1, 2, 3. I'm going to argue that's a really bad idea. You're agreeing with me? Why are you agreeing with me?
The lowest priority, the number 4, C4 is
The lowest priority is not aimed away from me. So I'm looking at the molecule from the wrong direction. So I would need to change my viewpoint on this. Okay? For me personally, again, this is how I would do it. Okay? I need that 4 atom to be rotated backwards. So what I'm going to do is rotate across that bond. That bond does not change its position. This is still 2. As I rotate to get that carbon backwards, what happens?
Becomes a line.
We could make 3 aligned. That's ultimately not going to matter. I would ultimately rotate a little bit harder to match this structure. Okay? So as I'm rotating this to go back to make this a dash, what happens to the OH? It's going to rotate out to become the solid. Because that's out here, we're rotating it to get it into that plane. What happens to the ethyl, that dashed one? And I don't want CH2, CH3. I want to label that as a 3. I can now go through and assign 1 to 2 to 3. Which direction am I moving? Counterclockwise. That's clockwise. You jerks. Clockwise. And that is R.
In the textbook, it had said that whenever maybe it was just specifying between the backwards and the forwards atoms, but it said that all you had to do was switch the R and the S, or does that not apply to this because our lowest priority is not pointing?
I have never consistently used that method.
Okay.
I can only teach you what I've consistently been able to use.
Okay. So just do it, draw it out, and it works best that way.
That's how it worked for me.
Okay.
Unfortunately, that's all I can give you. I'm not about to give you a method that doesn't work consistently for me, and I haven't consistently been able to fix that. Okay? And that could come from improper drawings. Maybe when I was trying to do those other methods, I was improperly drawing the structure, which means I couldn't translate it appropriately. Okay? I see you, David. Give me a second. The next kind of big thing that I've shifted to this is an eyeball. I could look down at the structure on this angle, and I'd be spiraling that way. I'd be going clockwise, which is R. For those of you having a hard time visualizing that, I'm trying to draw something in 3 dimensions on a 2D piece of paper with a bunch of 2D implements. Okay? Okay? So I've gotten so used to those wedges and dashes that I can interpret what the structure would look like in my head by just drawing an eyeball now where I'm visualizing it. Okay? That's because I've had enough practice with the model kits, and I get tired of taking 5 minutes to answer one of these stupid questions when everybody else can get it in 30 seconds. Okay? So I've tried to come up with other ways that consistently work for me. That requires a lot of spatial reasoning to be able to deal with. That took a lot of practice. Okay? If you want to use the way the textbook says, oh, you just shift it by 1. I think it worked here, right? It did. 1 to 2 to 3, which would be S because we did a rotation. It's an R. By all means, go for it. I just don't trust it. Okay? Kind of makes sense? Yeah, question.
So I was wondering about this one where you were looking at it in
This one and pointing,
sorry.
I need a little bit more.
The top left, the one we did first time.
Top left, yes.
Where the purple atom was going
Yep.
counterclockwise once you flip it. You just know that because your highest priority is coming at you, it's the opposite of what
That it's directly inverted, yep.
Right, so you're just like, oh,
Yep.
it should be.
That's that whole arm waving motion. Whereas if I turned and just showed me cycling to the side, it's not quite as easy to visualize. Right? And that's where that shifting comes from. Kind of makes sense? Okay. The last one we'll actually walk through. Let's see, does green show up okay? Yeah. There's our chiral atom. If we go through to assign our priorities, we're comparing carbon to carbon to carbon to hydrogen. So we can assign a 4 to our hydrogen. How do we tell the difference between the next? Well, we go out to a hydrogen, we go out to carbon, we go out to carbon, which then means
Hydrogen gets I3.
the CH3 gets our 3. Okay? And here's where things are going to go really sideways on us, distinguishing because on the next one. We might go through and say, well, they go out to carbon and carbon. Then we say, well, that would be the same carbon. We wouldn't be able to tell the difference. You're telling me you can't tell a difference between those two carbons? You can tell a difference. Okay, so there's got to be something else in there. That something else is rule. If we looked at the rule set, which I'm not about to just delete all this work yet, but if we go back like a couple slides on my slideshow to the rules, okay, what was it, D? Rule 1 sub 2 sub D.
Yep.
Okay. Assigning priorities for non-sp3 atoms. Okay. What we're referencing is that carbon has a phantom bond to a carbon. So if we go through and look at that topmost carbon, it is connected to 2 carbons and a hydrogen. Whereas the bottom carbon, I'll go ahead and show it in a different color, is connected to 2 hydrogens and a carbon. The top carbon is now connected to 2 carbons versus 1 carbon. The top carbon gets the higher priority. It's 1, 2, 3, 4. This means you have to bring in phantom carbons. And you could just say, well, can't I just say the less hybridized it is, the higher priority? Okay, so number 1, let's fix this. Assign chirality, R or S? S. Everybody see that? Cool. Changing the problem now. New question. Is my assignment of 1 and 2 still valid?
No.
Now my assignment of 1 and 2 actually inverts. Okay? The orange one is a higher priority than the green one. Why? The green one's connected to 2 carbons and a hydrogen. The orange one's 3 carbons. Bottom one takes priority. Okay? So we can't just say, making a blanket statement, less hybridized is more priority. That isn't always true. Is it true most of the time? Yes. In a bind on an exam, it's probably not a good idea to just say, well, it's probably going to be one of the most of the times. If anything on an exam, it's probably going to be not the most of the time, and you should be going with the other answer. Okay? Does that make sense? Okay. But going through the practice, you may notice less hybridization typically means higher priority. That is not always true. Okay? Questions about any of the work that's shown up there? Can I clear it all? What is the relationship between those top 2 structures? Stereoisomers is a fair answer, not good enough. There's not a bad answer. It's one or the other of these, yes. These are enantiomers. These are not identical structures. And if we go through to assign R and S, that first one we said was RR. Guess what the other one's going to be? SS. They are going to be named different structures. The R and S nomenclature system is what allows us to name these as different. Their connectivity is all the same, but the arrangement of the atoms in space changes. R and S allows us to see that spatial difference. Okay? or allows us to not to see it, but allows us to label it so that we know it's there. Make sense? Okay. So, are there other ways that we can visualize RNS? Yes. If you move into biochemistry, you'll probably encounter something along the lines of Fischer projections. And they may not actually call them Fischer projections, but that's what they are. Okay? A biochemist working with carbohydrates noted that when we look at carbohydrates, there's a lot of stereocenters. Okay? That means doing lots of RNS calculations, spin, flips, and rotations, and that sucks to deal with. Okay? But if we went through and did this, hopefully we'd be able to go through and find relatively quickly, let's see if I can do this. 1, 2, 3, there's our hydrogen as 4. That's clockwise, right?
Yes.
So R, let's clear all that work. 1, 2, 3. It's counterclockwise. S. The other one, we'll see, comes out as R again. The other last one comes in as R. Okay, don't stress about how I was able to do those faster. I just picked up patterns. Okay, well, we could go through and assign that for all of those, and that would suck and be tedious to do, but we could go through and do it. Okay, so if we remember this, because I'm going to end up deleting it here in a second, we had R, S, R, R. Okay, Fischer went through and said there has to be a better way of looking at the molecule. Okay, I would argue this isn't necessarily a better way of looking at the molecule, but fine. He took our line angle structure, which currently we're looking at it on its side, and he said, okay, this is what I want to do. I'm going to look at it from that side angle, okay? But I'm going to orient that carbon backbone all so that it looks like a straight line. Because right now it looks zigzagged. Okay? To make it look like a straight line, what does he have to do? He has to rotate the structure by 90 degrees out of the plane so that now we can't see the zigzag because the zigzag's coming in and out of the plane at us. Okay? So our structure would look something like this. Okay? We have to use a little bit of nuance to kind of figure that out, but what we're seeing is the zigzagging of that backbone coming in and out of the plane. And then we get the side groups. Okay? And we said, well, that looked confusing. Okay, so he did a little bit more adjustment and said that the substituents must always be aimed towards the observer. Okay? So if we take a look at that top carbon, the substituents, the things connected to our chiral atom, are aimed at us. So that, according to Fischer, is perfect. When we move to the next carbon, are the substituents aimed at the observer? No, so what does he have to do? He has to do a sigma bond rotation, because we don't want to mess with that one up. So we end up doing a sigma bond rotation right about here. Okay? And we get it, so that is now aimed at the observer. Okay? And we continue to go through and do this with the entire backbone until we end up with something looking like this. And he goes, well, that looks a lot cleaner. All the dashes are on the same axis, all the wedges are on the same axis, and this is lovely. Okay? The weird kind of bizarre aspect about this is if we now take this apparently straight-looking molecule and turn it back on its side, what does it look like?
Almost a ring, it's like curling all around. Yeah.
It's going to curl back on itself. So it looks awful from a drawing perspective. Okay? And if you think about this and look really carefully, you'll actually notice that this is spiraling backwards because I'm showing size here. That carbonyl is really, really big. The CH2OH is really small. It's getting progressively smaller because it's going further away from you. Okay? So when we're talking about looking at a Fischer projection, here's our eyeball. It's looking at that carbon. Notice the OH would be coming at it. Okay, how do we get the next position? Well, we move the eyeball. It's now looking here. And we move the eyeball. We're now looking here. And we move the eyeball. And we're now looking here. Okay? Get the idea of how he's getting to this drawing?
Yes.
Okay? And that may not be pretty or lovely, and why would we ever bother to do that? Okay? Anybody remember the assignment? The RS stuff? What did we say? R, S, R, R. R for right, S for left or sinister. Okay, you can go all the way back to biblical references if you want. Where's the largest priority group? Right-hand side. Where's the largest priority group? Fischer aligned the structure in such a way that he can assign R and S now very quickly just by looking at where that larger group is located. Is it on the right-hand side or the left-hand side? That's it. Okay, so we go, oh, that's actually kind of cool. That's not bad. Except that we had to go through this stupid rotational thing to get us into that viewpoint to allow us to make that assignment. Okay? If you have a bunch of chiral atoms, it probably makes sense to go through and do that effort. But more chiral atoms means more complexity, which means you guys complain. Okay? So what we'll do is pass the buck on to biochem and let you complain when you take biochem, and you can deal with the translation back and forth with Fischer projections. Okay? So, because Fischer has now defined his drawings to be this way, doesn't have to use wedges and dashes anymore. He's saying, when we're looking at a Fischer projection, it must be where the backbone is always aimed away from you, which means I don't have to specify dashes. Okay? It must be that those substituents on the side chain, on the main chain, are aimed towards you. Well, if that is always true, then I don't have to specify it. And I can just show it as this little cross-hatched lovely thing. Okay, for the record, I did not draw that. I stole that from the internet, and I have to point that out for what reason?
Oh, yeah.
Okay, I've yelled at a few people for drawing that. You can't draw that. That's saying hydrogen is connected to carbon and oxygen. That's not true. Okay, draw it properly. Okay? So, that makes things really go through, or really easy to deal with. Okay? Lower right-hand corner, we get a little note here. There is a new labeling system that you'll see in biochemistry, referencing capital D and capital L. Capital D for dextro, capital L for levo, whatever you want to call it. Okay? levo is representing left, dextro, right. So you might say, well, why aren't those R and S? Because it's an entirely different nomenclature system that has nothing to do with R and S. The D and L have to do with the penultimate carbon, the last chiral atom. That last chiral carbon, where is the higher priority substituent? If it's on the right, we call it D, dextro. Okay, so if you hear reference to D amino acids or L amino acids, that's what they're referencing. It's that, quite frankly, moronic nomenclature system. Okay, it's actually not moronic. They have decent reason behind it. Okay? But it has nothing to do with R and S. I can't assign any of those other chiral atoms D and L. Okay? Different nomenclature system. Kind of makes sense? Questions? Because I started to see some hands. Okay. So that's the point of Fischer projections, is to rotate carbohydrates so that we can actually assign R and S relatively quickly and easily. It also allows us to make this assignment of D or L in the reference of carbohydrates really easily as well. Okay? Why might this have been important to Fischer and carbohydrates? Because we think carbohydrates and we think glucose, right? Okay. There's a lot of carbohydrates. Okay? And this is just one branch of the carbohydrate family tree. Notice every one of those crosses is a chiral atom. To go through and assign R and S when it's drawn out as a line angle for every single one of those, that's going to suck. Okay? So we came up with a different system to go through and organize that. Okay? What's extra fun about this is the nomenclature system behind this. Imagine like the worst naming system ever, like naming individual people by their, just inventing a name for them and then naming them that. Welcome to biochemistry. Oh, I think that looks like a urethro, so I'm going to call it a urethro. Seriously? Yeah. Yeah, it's awesome. Okay. So let's not deal with that soapbox too much more. Physical observations of these. Okay. Let's take a look at diastereomers. So if we look at the molecules shown here, these are diastereomers of each other. If we compare the overhead view, kind of the side by side, we'll notice that one of the stereocenters did not change and the other one did. Okay? So that means we have diastereomers. They're non-superimposable and they are not mirror images of each other. Okay? But they still have all the same connectivity. We could also turn it and look at it on its side, which I didn't explicitly talk about. Right? Kind of left you guys in the textbook. What kind of view am I looking at now? And don't say on the side. Begins with an H. Haworth, Hayworth, something with an H, worth. Okay, I don't know how to pronounce it. Okay, we're just taking the structure, looking at it from the side, and visualizing it that way. Would we expect the physical properties of these materials to be different or the same?
Different.
Why should they be different?
They take up different space.
They take up different space, which means if I'm going to pack multiple ones near each other, they're going to stack differently, which means I get different. Arguably, we don't get any reactions with these. Officially, we haven't covered that yet, but we will talk about it. What is a common property that we've talked about, physical property? Melting points and boiling points. These are going to generate different melting points and boiling points because they're going to stack differently. That's like trying to stack chairs versus tables. They both have 4 legs and a little seat, flat part, but they're going to stack differently. Okay? Same thing is going to happen with our diastereomers. Okay? So we see different melting points, different boiling points. Their interactions with the outside world will be different. Okay? Which means we can easily separate them. But what happens if we switch to now enantiomers? Okay? When I look just at the enantiomer itself, is its arrangement different than its mirror image just with itself? It's a really hard question to visualize. If I stack a bunch of right hands together versus stacking a bunch of left hands together, is that stacking going to look different? If it's just lefts and just rights, they're going to look identical. I'm not going to see a difference. Which means what happens with their physical properties? They're the same. Well, if they're the same, how do we get them away from each other? Okay? If they're the same, why do they interact differently? For instance, we look at naproxen. S-naproxen is an anti-inflammatory. R-naproxen destroys your liver. Oh, kind of a big issue. Okay? R-limonene smells like citrus. S-limonene smells like turpentine. Okay? That's kind of a big difference. Oranges or the gas station. Okay? That's kind of a big deal. Carvone smells of mint. S-carvone smells of caraway. Okay? These are some pretty big differences. Okay? If we just said their interactions are identical, why are we seeing a difference? If I take R's or right-handed scissors and I stack them all with each other, they'll all stack somewhat neatly. If I take left-handed scissors, they would all stack somewhat neatly next to each other. How would I tell a difference between a left-handed pair of scissors and a right-handed pair of scissors?
How they fit in your hand.
How they fit in your hand. What is your hand?
Left or right.
Left or right. Your hand is chiral. Why can we distinguish a difference between these?
Because they're chiral.
We are chiral. Virtually everything in biology is chiral, which means we will distinguish these based off of their different interactions. R-carbone fits differently into our nose receptors than S-carbone, which is why we acknowledge R-carbone like mint and S-carbone like, what is that, caraway.
It's a spice.
Okay?
The seeds and
Yeah, I know what they are. I couldn't remember the word. Naproxen. Naproxen goes through what is it, an NSAID? Is that right?
yes.
So it does something NSAID. The R-naproxen doesn't do that. It goes and attacks your liver. Okay? Our liver and our NSAID things, okay, very sciencey there, okay, are chiral, which means those drugs will interact differently with a chiral substance. Okay? That's where these things get different and interesting, is how they interact with that external chiral system. Yes?
I mean, it's non-steroidal anti-inflammatory drug. There you go.
I prefer NSAID. Okay. So enantiomers are problematic. If I go through and I make a single enantiomer, but I don't know which one, and I attempt its melting point, the melting point for S and R are identical because they have the same interactions in themselves. So I wouldn't be able to know which one I had based off of the melting point because they have the exact same intermolecular forces. They're just mirrored. Okay? So I need something that allows me to distinguish them. Okay? And that becomes challenging with enantiomers. Okay? The way we end up doing that is through a couple-step process. Number one, don't make them. Okay? If you're running a reaction that results in enantiomers, a good idea is to not. Just don't do that step. Find some other way to run the reaction where you don't get both products. Okay? And as we will find later in the semester, when we run reactions, there are some reactions that will always produce enantiomers. Okay? And if that's our only option, then we need something else to separate these away from each other. Okay? So one way, separate them on a chiral medium. Okay, what does that mean? That's effectively what the human body is. It's a chiral medium. Okay? So we just give the mixture of drugs to a person. When their liver fails, we just throw that part away, and when the rest of them dies because they don't have a liver, we'll just extract the drug out of that. Okay? That's not the best idea. We can create chiral mediums. We can create pure substances that are optically, or I can't use optical yet, chirally pure, that are just R. That will allow us to distinguish the difference between those enantiomers and separate them away from each other. So we have to use a special medium. Okay? React both with a chirally pure compound and then just separate. Okay? 3 is just a fancy version of 2. 2 is saying don't actually make any bonds, don't do any chemistry, just kind of separate them. Okay? How do I distinguish left-handed scissors from right-handed scissors? Well, I take a right-handed person and I give them a pair of scissors. Does that hurt? Okay, that was the left-handed ones. Was that okay? Those are the right-handed ones. Okay? We aren't doing any kind of chemical interactions. Okay? In 3, we're now doing a chemical interaction. We fuse it to something else. Okay? But the hope is that when we fuse it, we create a product that we would be able to separate. So what is the relationship between those two products? Okay. As a hint, let's take a look at the easy one in the middle. Pen work. Seriously? Yeah, apparently I ran out of ink. What is the chiral atom in there? Sweet mother. What is the assignment, R or S? Oh man, you gotta go through and assign priorities. That's 1, that's 2. It's R. It literally, it says so right there. What happened to it in the product? It's still RR. Okay? If we take a look at those first two starting structures, what's the relationship between them? These two are enantiomers. Okay? So one of them will be R. 1, 2, 3. There we go. That one's R. Look at that. That one's S. When we go through to form the product, this one would still be R because it's that wedged one. The other one would be S. What is the relationship between those products? Like, I can't figure that out. It's too hard. R, 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 S, R, R. What's the relationship? They're diastereomers. What is special about diastereomers? They have different physical behaviors. I can now separate these two compounds because they behave differently. I could crystallize and get one of them to crystallize, the other one to stay in solution. Okay? I could separate them on a column. I can separate now normally without having to stress about anything. But the whole point is that I wanted those individual compounds back. How do I get them back? Because right now what I've got are these things. And now I can separate them. But I want back to my original species. How do I reverse that reaction? Yeah, we haven't talked about reactions. You've talked about this one. Most of Gen Chem was spent looking at this reaction. I'll accept that. It's a neutralization. It's an acid-base reaction. Okay. What is the functional group on tartaric acid? So carboxylic acid. What did we do? We added an acid and we did an acid-base reaction. What do I have to do to reverse it? Add a base. Okay. So all I got to do is do the opposite of what I just did, and it'll revert immediately backwards. This is why acid-base reactions are fantastic. They are easily reversible. Why did my pen die? I'm kind of irritated. Yeah, 0%. Battery's dead. Sweet.
I'll give you mine.
Okay. No.
Worth
Okay.
a shot.
So, the last thing, give up. I can't separate them, but I'm at least going to report that I screwed up. Okay? And so what we would report is what is known as the enantiomeric excess. How much more of one did I make than the other? If I made them equal amounts, what's my enantiomeric excess? 0, because it's a difference between them. Okay? So if I see a 30% enantiomeric excess, I actually made only a preference for one than the other. Okay? So I would just report that excess. That's it. Kind of, sort of? Okay. How do we know? Because at this point, how do I know this one was R and this one was S? A little finger waving, cool. You did a finger waving and you're pointing at what?
The chiral.
The atom, right? But when I run an experiment, how many structures do I see? Here's a beaker. When I look in that beaker, there's a solution. How many molecules do I see in there? None. How do I know which one's R, which one's S?
Test some of it.
I could test some of it. Here, Dave, take this.
I would rather
It might destroy your liver. It might fix your headache.
test it like this way. Like what you did here. You take a small amount of it and react it in order to get
Okay, so there's an idea. I think I made mixtures, so I'm going to go through this process to try and make new compounds that I know I'd be able to separate and then separate them. What if it was pure to begin with? What did you just do?
How much work?
A whole bunch of work that did
Unnecessary.
Well, I told you that.
nothing. It could have told you that it was pure. That's cool. Okay? But at the same time, what are you going to do to the amount of product?
Lose some of it.
You're going to lose some. Okay? And you could decide liver damage versus headache relief. I'll risk losing some. Okay? If we were all nice people. Okay? Ideally, we have a faster way of discovering that. Okay, we do. Interestingly enough, chiral atoms interact differently with light. All we got to do is shine light on them. Okay? That light has to be of a particular sort. It has to be polarized. Light moves in waves, so it goes in all which directions. So what we do is we take our light, we filter it out so that we get one wavelength of light. Okay, that's the whole point of this filter. We then pass it through a polarizing filter. And so what they're showing here with this orange thing is that it is orange light. Why orange light? Because when we do this, it's typically done with the sodium D line. What color is sodium D?
Orange.
Orange. Okay? So it has all vectors of light. We pass it through the filter, and what happens? It's now only one vector of light. Okay? And if you think this is kind of bizarre and interesting, you probably have polarizing sunglasses, right? Or at least heard of them. If you take two of them and turn them 90 degrees from each other, what happens to the light? Nobody's tried that?
It goes away.
It goes away. You get no light because polarized lenses filter out a one or all other except for one. If you take another pair of lenses and you turn it 90 degrees, you're filtering out one light into one path, and then you're taking the other pair and filtering out all of that, which means how much light passes through? None. It's actually kind of neat and fun. I've done it all the time. Okay? So we get this polarized light. Okay? It's now all on that vertical axis. If our sample has a chiral molecule in it, that polarized light hits the sample, hits the chiral atom, and it goes, whoa, that's weird, and it turns. The more molecules it hits, the more the light shifts. And so what we end up seeing as we pass the light through the sample is that that light will slowly rotate off of that axis. We can detect the final rotation. Depending on how far it is rotated, we would then observe that as either positive a degree off that vertical axis, or a negative rotation off of that axis. And we call that negative and positive for levorotatory and dextrorotatory. Not to be confused with the capital L and capital D of the biological biochemistry nomenclature system, because that's something else. Okay? This is also not to be confused with rotating right on a structure and getting R, and rotating left on a structure and getting S, because that's also an entirely different system. This plus minus is solely experimental. I have no idea the structure of the compound in there. Okay? All I know is that whatever it is, it rotates light to the right or left. Okay? Because it is rotated light, I do know one thing about that compound. It must be chiral. Okay? And that's it. That's all I know, is that it is chiral. That does not mean there's only one chiral atom. Okay? I could have two chiral atoms. Okay? I could have three. There could be an infinite amount of chiral atoms. Okay? What if it doesn't rotate light? Then that sample is achiral. That's our word, achiral, not non-chiral. Does that mean there's no chiral atoms? No. Because a compound can have chiral atoms and yet be achiral. For instance, meso compounds, if there's an internal mirror plane. Okay, so we have to be a little bit careful with this. All it says is the molecule is chiral. Okay? And arguably it's not even that. It's the sample is chiral, or the sample is achiral. Okay? Yes?
What would happen if you had an equal amount of...
We'll cover that in a second. Okay? So this achieves our minus and positive. This is not the same as R and S. Okay? Positive could be R, it could be S. Don't match them up. Okay? Once you are told for that molecule R is positive, then we know the S is negative. Okay? But you have to have that information to be able to make that assessment. Okay? Things that are kind of important on this, we get some formulas. EE for enantiomeric excess. So we can calculate it if we knew the percentages of each of them. We can also calculate it based off of the optical activity. Okay? Remember, the light rotated every time it hit a molecule, which means if I have more molecules, more rotation. So I'm going to have to come up with a way to normalize the amount of compound to the rotation. That's that formula on the far left. Okay? This far left is the specific rotation for your compound. Okay, will be equal to the observed rotation. How far did it actually rotate when we saw the light? Divided by the concentration and the path length. The more path length, the more likely you encounter a compound. Okay, so we have to take that into consideration. Okay, concentration measured in grams per milliliter. Why? It's fun. Moles per milliliter was taken. Okay, length is usually in decimeters. Why? I don't know. That's how it was done. Once it's been done, we have to deal with it. Okay? The enantiomeric excess is the specific rotation for whatever you're testing divided by the specific rotation of the pure sample. Okay? So a pure R is going to have one specific rotation. A pure S will have the negative, but the same numerical value. Okay? Because they respond to light the same, they just respond oppositely. So, what we're talking about here is optical activity. Do they optically, light, interact with light? Okay? If they are chiral, yes, there's optical activity. If they are achiral, then no, they don't interact with the light. An R enantiomer, should that interact with the light? Yes, that is a chiral compound. That's why we call it an R compound. Okay, a meso compound. Why not? Oops, sorry. A meso compound is going to have two chiral atoms in it. One is R, the other one is S. Because both are present and there's that internal mirror plane, the light comes in, hits the R, rotates. What does it do when it sees the S? It rotates back the equal direction, which means the net result is no optical activity. That was a mouthful. How about a mixture of enantiomers? 1 to 3. Okay, yes, there's an excess of the R. Okay? In the case of the meso, it was 1 to 1, 50-50 in the same compound. Now I'm saying I have two different compounds. Some of them are S, some of them are R. Okay? When it goes through, I am going to see some optical activity. How about if I have a 50-50 mixture with one R and one S? No. Okay? Now when it goes through, it sees the R, rotates one direction. When it sees the other molecule that is S, it rotates the other direction. So when I said we have to be careful when we're looking at this, we're determining the optical activity of the sample. The sample could be one molecule. It could be multiple. Okay, so we have to be a little bit careful when we're looking at optical activity. Okay, so a mixture of enantiomers is 1 to 1. Whoops. No optical activity. A mixture that has 0% enantiomer excess. Isn't that the same as D? Yes, it is exactly the same as D, but it's another way to phrase it that then confuses people. Okay, so also a no. Okay, we can add another one on here, a racemic mixture.
Yes. It has a mixture. I don't know.
It has a mixture, so you're saying yes, it should be chiral. What did D have?
It had a mixture, but
And that was?
full mixture.
Okay. So the answer to a racemic mixture is going to hinge on what?
The ratio of an atom.
What does racemic mean?
I have no idea.
I don't know.
Okay, if you don't know what racemic means, that's the problem. What does racemic mean? So I think you started to say it. No? Oh, I thought you guys did. It's a 50-50 mixture. It's 1 to 1. It's an equal proportion. A racemic mixture is D. These are one and the same.
D
And F. Oh, and E. Yeah, you're right.
so
They're all
saying the same thing.
saying the same thing with different words. Okay? Racemic is an adjective. You could turn it into a noun by calling it a racemate. Okay? So there's a bunch of derivations of the word racemic. I don't remember what they all are. All I remember is the racemate one. Okay? They're all getting at the same thing. You have a 50-50 mixture. Okay? This gets a bit exciting, involving a bunch of calculations and all this fun stuff. The specific rotation of that compound is plus 15.9. Determine the percent composition of an enantiomeric mixture of 2-iodobutane if the specific rotation is negative 3.18. Okay. So the percent composition means I want to know, in this case, the percent S equals and the percent R equals. What I'm asking you to do is to identify the exact numerical value, okay, which you can do. It's a bit of algebra. It really isn't that bad, but it tends to throw people for a loop. Okay? So multiple choice, let's see if we can figure this out without doing too much number work. Okay? Number one, I thought plus and minus had nothing to do with R and S. How could I possibly tell you the percent S and the percent R? Plus is dextro. That is not R. How could you tell me plus or R and S when all I've given you is plus and minus?
The question says 2S.
It says the 2S is plus. Okay, which means R is negative. Okay, I did give you that information embedded in the question. R is now negative, S is positive. Okay, so you could assign R and S based off of those. Okay, what else could you tell me? Just looking at the numbers. What do you think about that mixture? Is it a 50-50 mixture?
No.
Why not?
There's a greater amount of R.
Okay, I'm going to come back to you in a second. What did you say? We don't necessarily know that yet. What did you suggest?
There's a greater percentage of R.
Okay, so you're actually taking it a step further. Okay, what do you have?
Did you say that the S rotates more than R?
No, unfortunately, S and R will rotate the exact same. The exact same numerical distance. So if I look at the 2R iodobutane, it's negative 15.9. Okay. Why did you say R was larger?
I might have done that wrong. I was just
No, you didn't.
thinking, because if the S is positive, but the overall mixture is negative, then obviously the R has to be greater.
Okay. Is it a 50-50 mixture? If it was 50-50, what happens to the optical activity? It goes to 0. Is it a 50-50 mixture? No, because it's not 0. Okay. Well, which one do I have in excess?
R.
Why is the R in excess?
Because there's more data.
It's rotated more the negative direction, which means when I look through at this, I'm going to expect a larger percentage of R than I will of S. How much more? A lot more? A little more? Why only a little more?
It's only a little negative.
It's only a little bit different than 0. Okay? That information could allow me to kind of process my way through some multiple choice answers, maybe even get me to an answer without having to do any mathematics. What is all the mathematics? Damn it. I didn't show any of the mathematics. If you want to see the mathematics, you can talk to me after class about it. The big concepts I want you to get out of this. S and R and plus and minus are unrelated systems. Plus and minus is experimental. R and S is structural. You're looking at a physical structure. Okay? If pure S is plus 15.9, then pure R is negative 15.9. It is the exact numerical value, but the opposite direction. Okay? Plus S and plus R, or sorry, percent S plus percent R has to equal 100%. That last equation is what allows you to solve all this. And it's that last equation that most students don't remember when they go through to attempt to solve. With that, we have to be done, okay, for today. We will be talking about our other forms of spectroscopy this Wednesday, Monday, and next Wednesday is the exam. Yay, yay. Okay, so